If you are in Twitch right now, !notes is going to give you the Google Drive where I keep all of my discussion series notes. If you are on YouTube, it will be down in the description below. So on Wednesdays, we do discussion series courses where basically I will read through a bit of a textbook, write a bunch of notes, come to stream and teach you all what I've learned. And today, we are going to do a discussion series. We're on like part 8 or 9 or something. Oh, wrong camera. I've been away, okay? Cut me some slack, okay? Today we're working with Nielsen and Chang-book. We've been talking about the linear algebra necessary for quantum computing. So let's do a little bit of a last time. Last time we introduced states as vectors. It's not often that you hear about, like states have a unique property in quantum mechanics, right? They have a, this is the Dirac form versus the Pauli matrix form, right? Dirac works with bras and kets. Pauli works with matrices and vectors. And this was two different ways of seeing the same thing. And we introduced last time, which was a few Wednesdays ago now, 2 or 3 Wednesdays ago. Nice day. And we introduced states as vectors. We outlined many rules for vectors that follow in quantum mechanics, things that we're going to need, like addition, multiplication, conjugation, adjoints, and things like that. We had a table and I'm going to write most of this table on so that you can have it from memory. Again, this will be in the notes. This table is from our last time too, which is the notes, ! Notes, if you want those. The notes, or you can go to Discord. There's a section on Discord where it has discussion notes where you can get the link from there too as well. But basically, the idea was we had this table. We had complex conjugation. Complex conjugation, which basically would take a z. If z was equal to 1 minus or plus I, then conjugating z, complex conjugation of z, would basically be just switch out the sign that's in between the 1 and the I. Namely, I guess a more closed form would be if z is equal to a plus ib. Then a conjugation is what you do. You want to change the sign in front of the complex term. Okay? That's conjugation. And it will be relevant today, to some degree. Now, what else do we have? Well, we also have the ket. Oops. The ket, which is the state, of course. We had a bra. We had the inner product, which we're going to talk a bit more about today. I know I kind of put it off last time, but we are going to talk about it more today. And then last thing we talked about was adjointing. I'll just give you an example of an adjoint. If you have a matrix A, B, C, D, then the adjoint of said matrix is going to be the complex conjugate of every single element. So A star, B star, C star, and D star. But also notice another thing you do when you adjoint is you do the transpose, which is basically if you just flip every element, the indices of every element. So one way you can do that, like thinking about it, is draw a line through the diagonal and flip everything. Another way of thinking about it would be like if you have an element ij, then the transpose, or the adjoint of ij, the transpose of ij is going to be AJI. Okay? But we also talked about what a basis is and how looking at a basis of a problem, we can look at multiple different bases to get a different view of the problem. And that's also, that we also talked about the spanning set and how that works. And last thing we talked about was the linear dependence / independence of having one of these spanning sets and bases. So today, we're going to talk about matrices and operators. Now, we talked before about how states can be vectors. We talked a lot in the earlier discussion series about operators, but we didn't ever, like, I know I showed that, but the authors didn't really introduce a way to talk about it in matrices form. Basically, a Pauli matrix notation. So the authors take the time to do that right now. So linear operators and matrices. So linear operator A on a vector space will basically so this is we're going to define A by basically the mapping from V to W. It's going to be the mapping from one vector space onto another vector space. And then we're going to, it's true, scary math. Hi, Natty, good to see you. Yeah, it's basically like, how do you take one vector space and transform it into another vector space? What type of formulas or functions or whatnot can we do with this? And so so let's go over some things. If we had, if we want to apply the matrix to some set of eigenvalues and eigenvectors, which we're going to talk a lot more about next. Maybe I should just say some scalars and some vectors. Vectors in a vector space. How about that? Then the scalar will come out, obviously, and we'll be left with just the operator acting on the vector space. That should be, or vectors themselves, that should be something that is denoted as something very important to a linear operator. Two more important linear operators that we're going to use a lot are one specifically that we're going to be using a lot, and that's the identity operator. An identity operator, how do you think that's going to map the state of V's? If we have a vector space with vector V's in it, how do you think the identity operator is going to map those? What would be the set W that we're going to be mapping in? Yeah, to itself, exactly. It's just going to go back into V. This is going to be a very crucial thing. If you've taken a quantum mechanics class, you know that when you do quantum mechanics, you popping in identities everywhere. You're like identities like, like this. Or whatever. I don't know whatever it is. You guys get the picture. Or like the summation of the identity. I probably should have written it down so I remembered the exact notation. But you guys remember what it is. Another one that's important is going to be the zero operator. The zero operator will apply to the V vectors, and that will become a different set of vectors, namely zero. Less impressive and less exciting, but nevertheless true. This is considered linear algebra. Yes, this is the linear algebra that's necessary for quantum computing. It is quantum mechanical in general, but we're only going to be touching the stuff that's necessary for quantum computing. Now we can consider three vector spaces. I guess let's have a fresh board for this next one. Our vector spaces are going to be VW and X. So consider three vector spaces and two operators. One that takes V to W, and one that takes W to X. Okay? We can talk about the composition of B with A. Basically, it's like an ordering of how we're going to, attach these operators to vectors. So we can write down. This is again notational. I think composition. So composition is not the same as multiplication. Composition. That took up a lot more space than I thought. Would be like f of g of x type of deal. That's a composition of two functions. Not a multiplication of two functions, but a composition. And then basically one way we could think of that is if you want to do B and then A against the vector space V, that would map vector space V to W for A. So then we would have, V would be applied, or A would be applied onto V. That would map from B to W. Then B would be applied to W and would map W to X. So this would be how you would take from V to X, right? Through two-step. An important note here is that the linear operators are best understood as their matrix representations. I mean, these are, again, I told you we were going to be talking about these linear operators as matrices. Matrices are also easier to do things if you're unfamiliar with how the operator system works, right? You have, when you learn quantum mechanics, I've talked about this a million times, when you learn quantum mechanics, it's a language. You learn about states and vectors and then operators and matrices. Most of the time, people are just going to stick with vectors and operators, or vectors and matrices, because that's what they're comfortable with. So this is another benefit of having that, but also that linear operators are, in fact, equivalent to matrices, but I guess there might be something else about operators that would make them less true. So if we want to have so let's talk a little bit more about what we can do with this. Let's say, let's talk about how we can see this linear operators as matrices. So if we have two vector spaces, let's have A being the operator that takes V to W again, that old shtick. We'll have V has a basis of V1, V2, up to Vm. And W will have a basis of W1, W2, up to Wn. So we can have some n by n matrix A such that the operation on Vj will be equal to the sum of all of the matrix elements Ij on the vector space of W. Okay? So again, this is just equivalent, like showing the mathematics behind using an operator as matrix, basically the elements applied to each element of J. And like there's some tensoring of indices here, if you're going to be so bold as to do that. I mean, not everybody is a tensor, is a level 14 tensor boy. I am not. So I kind of steer clear of that, but some people might be very comfortable with tensors. Of course, this is not the nicest notation for that, but chat's in the way. Why is chat in the way? Apologies if you were trying to see that and chat was bothering you. Chat bothers me very rarely, but I imagine it was bothering you. So, but yeah, so this is just the mathematical underpinning of taking each of the elements, summing over all of the elements of the matrix Ij applied to the appropriate element of the W vector space. Okay, so, and these lines are decorations which just tell you the Q area? Yeah, so that's exactly right. The bracket notation, I'll show you that, is a bracket that make all the work a lot more simpler. So instead of needing to write down the vectors every time, like in quantum computing, you'll see they're only like a two-dimensional, we'll talk about Hilbert space next time. But in quantum mechanics, if you only have like one qubit, you're only in a two-dimensional Hilbert space. So it's just like an up or down, or like the two possible states are going to be 1, 0 or 0, 1, which is nothing really in the terms of vectors. So it's not hard to deal with. But now suppose you want to, but we're talking about quantum computers with like what, 32, 64 bits, some 256 bits of information, or of qubits, right? So now we're talking about not having 2, but having 2 to the 264. So, of course, you don't want to write vectors. You don't want to write vectors. You don't want to write vectors. So the easier way to do that would be to get comfortable with the bracket notation, where you can just write one thing that includes everything. So, like, it doesn't matter how many vectors make up these vector spaces. We just have this nice, concise notation like this. And I'm sure there's cleaner notations than writing this 252 to the 256 characters long. Like, obviously, mathematicians don't write vectors like that, but you get the point. You get what I'm saying. It's a lot cleaner of a notation for quantum mechanics. And like I said, physicists just take everything and use it how they want. So okay, so let's keep going. We have to show our fancy pants boys. I'm just gonna get rid of this really quick. I want to show you the Pauli matrices. Why? Because Pauli matrices are everywhere, and some people might not know the Pauli matrices. We'll introduce a couple notations for the Pauli matrices. The zeroth Pauli matrix, which some people might not be too familiar with, it's just the identity. A lot of books might not even show you the zeroth Pauli matrice. Then there's the first Pauli matrice, which is the sigma in the x direction. I wonder how many people could just spout these off at the top of your head. I did, but I studied statistics. I'm not sure how many people studied statistics. I would also not be 100% confident. I would be confident with the y, because The only thing I'm unconfident about the y is where the minus sign goes. That's what I meant to say. The x is easy because there's no minus sign. The z is easy because it's used far more than any other one. And the only one I'm a little bit always unsure of is where the negative comes from, or which value is negative in the y matrix. Poly matrices are bread and butter of quantum computing. 100% they are. I mean, like, we introduced, like, the X gate was one of the first gates that we introduced. The Z gate is also one that's, like, wildly useful in that. I don't know how much the Y gate is, but maybe. But yeah, so these are definitely going to be tremendously useful. What was X's analogy? Was it just swap? Yeah. Oh, maybe it's just not. Oh, it's with the not gate. That's what it was. Yeah. Y is just the after rotation. True. Y is useful for rotations, and when Y is just the after rotation. Cool. Yeah. We'll see it, I'm sure. But this was just a not gate, if I remember. Yeah, not gate. Okay. Cool. I think my kids are coming home on a bus now, or is it just another loud vehicle? Nope. More loud trucks. All right, so then let's talk about inner products a little bit. Almost done with today. Like I said, nice short lesson. Inner products are like dot products, but they're not dot products. I think a dot product is like a simplification that we teach undergraduates because inner products are difficult. But we're going to only talk about the things we need to know, basically the notion of how to write them, the notation for what they are. An inner product is when you take two vectors from a vector space and produce a complex number as an output. So, for instance, if we have so we have to have two vector spaces, two vectors of vector spaces. We're going to use the conventional notion that our inner products are going to be written like that. The book uses a bunch of weird inner products where you're like taking like V. It's like this or something, which I don't know. If you are following along the book, we're not going to be doing that. I'm not sure why that. I'm not sure where they came from and thought that was a more convenient notation than this, but I don't think it was a quantum mechanical background, because that's very confusing. But it's interesting to see that for most intensive purposes of what we'll be doing, we'll be kind of just treating a inner product like a dot product, where you're summing over the multiplication of all of the matching up terms and the indices. Let me go to the textbook really quickly. There's three things that satisfies the requirement of an inner product that I missed in the notes that we'll have to add. The first is that the dot product is linear to the second argument. So, for instance, if we have, oh man, they do not make this easy. I didn't transpose anything into their language, or out of their language. So let's just use this notation for the starter. We have V, comma, and then if you have some eigenvalues of this other vector space that you're dot producting together, you might find that the scalars, that it's linear, so that the scalars will come out of it. And I think my kids are home. But the second thing is that now I can use our other notation. That that if you complex conjugate it, it's equal to the reverse order of the inner product. Like this. And lastly, that if you take the inner product, of two vectors in a vector space, in a similar vector space, that it is greater or equal to 0 with equality if and only if, let's see if I remember how to do that, the vector space is 0. let's see. The last thing I wanted to talk about is orthogonality. I can't believe I didn't put those in my notes. Like I said, I'll have to add those before I upload. But those are the three things that you need for an inner product. You want linear. You want linear in the second argument. You want the dot product to be equal to the complex conjugate if you switch the vectors, the order of the vectors. And then lastly, if you dot it with itself, it should be greater than or equal to 0. Equal only if and only if the vector is in fact 0. Okay, so let's talk about orthogonality. Orthogonality is the last thing we're going to talk about today. Orthogonality is, again, about inner products. We're talking about inner products here. And what happens when the inner product of two vectors is 0? So if we have an example would be if W was equal to the vector of 1, 0, and V was equal to the vector of 0, 1, then if we were to dot the two together, you'd have 0 times 1 plus 0, or 0 times 1 plus 0 times 1, and we would get B0. But we could also talk about norm. A norm is defined to be, so this is orthogonal. When you have orthogonal, I skipped ahead a second. Orthogonal is when you have the dot product between two vectors, and it's equal to 0. That means that it's the same thing with the dot product, that they have the orthogonal, they make a right angle, and it can be very useful. Hey, Ethan, good to see you. But last thing I want to talk about is norms. We want to normalize a vector space. Norms. A norm is going to be written notationally as such. Basically a state with double lines on either side of it. And that's going to be equal to the square root of the inner product. Now, if it's normalized, then this then the norm is going to be equal to 1. And normalization is a very important thing we do. Why is normalization important in quantum mechanics? Because normalization is how we ensure that our states, the probability of measuring a state, the probability of measuring all the states, I should say, adds up to 1. We don't want a situation where the probability of measuring all of our states does not add up to 1. That doesn't make sense physically, because you can't have, more or less than 100% chance or outcome, right? So the idea is we want to make sure that if we normalize it, everything normalizes to 1 nicely. It's a very important process in quantum mechanics. Another way of writing it mathematically would be like if we had a bunch of vectors, then they would be normalized if the following was true. The set of vectors I are orthonormal. I should say orthonormal if the inner product is equal to 1 when the vectors are the same, and 0 if they are not the same. Okay? And then I could say one note about what happens if you get a group that is not normalized. And one way you could handle that is in order to get them into an so if, let's see, so it can be, is one method we're not going to show on the board or talk about, but if you're interested, it's a Graham-Schmidt method. I've actually used it in research when I was an undergraduate. But it can be used to produce an orthonormal basis set. So if you have a set of vectors that are not orthonormal and you need them to be orthonormal for a procedure, like I said, I've used it when calculating normal modes. When you're looking through like phonon vibration inside a material, you might get a weird set of vectors that for whatever reason might show up to not be orthonormal. You need it to be orthonormal, so what do? You normalize it using a Graham-Schmidt process or another process that might be more beneficial, but Graham-Schmidt is kind of like the textbook way of doing it. Other than that, I don't know how much the authors plan on using it, so I wasn't going to put it on the board. But next week, we're going to talk more about Hilbert space, the Cauchy Schwarts Inequality, and eigenvectors and eigenvalues. But that's it for today. Just some more fun with vectors and matrices, talking about the inner products, we talked quite a bit about the inner product.